Hey guys, welcome back to another video. Today we'll be using P5JS to create this cool effect here by Dimitris, in which he took an image of a classic painting and subdivided it based on pixel density or color density and got this really cool abstract looking effect. And we could also make a 3D version of the subdivision of the plane, but it is more complex and requires extrusion algorithms and subdivision algorithms of a plane rather than overlaying shapes over one another. I did try the 3D version in Godot and Blender, but they seem too complex and the learning curve is so steep. So I thought I might make this video first and try the 3D version later on. So let's get into it. So the algorithm itself is based on recursion and it uses a data structure called KD trees. Now KD tree is a binary tree data structure, which means we have a root node that contains the k dimensional points, so x and y in our case. It could also be z and other dimensions as well. So this is going to be our root node, and each node subdivides into two other nodes, and you could call this subdivision or children, and it keeps going to two other nodes and two other nodes. Okay, so now let's get into the overview of the algorithm or how the algorithm works. So first we'll have a rectangle, and this rectangle is going to be a vector shape. So we'll have xy, xy, and xy, and I'm going to keep dashes here. Okay, now this x and y coordinates are going to be based on the image width and height, so we have a 1-to-1 ratio to work with, and the starting area is not different from the input image, right? So this is going to be our starting plane or rectangle. Now the method we'll be using to subdivide the plane will be a recursive function. So at the starting, at the ready function or the setup call, we'll create a function and we'll call it with a depth value and the vertices, right? So we have vertex 1, vertex 2, vertex 3, and vertex 4. And all these vertices together will make this area. And we'll call this tree. And we'll give in v1, v2, v3, and v4. And the depth initially is going to be 0, and the vertices are going to be the x and y of the rectangle or the image we gave in, right? So if the image is a square, we'll have xy the same here. So as I said, we have to have a 1-to-1 relation with the image and the rectangle. Now the conditions for subdivision are really simple actually. We take the average color of the region, so we go through each pixel within the region and add them all up and divide by the number of pixels in that region, so we'll get the average color. And then again we'll go through each pixel and compare the average color with another function called the difference color function, which will give you the difference between each color. So if you're given two colors, it will spit out a value, and that will be the difference value. So I'm going to make a function here. So this is going to be our difference color function. We'll give in color 1, or we'll just call this color and the average color. So we have to loop through the entire pixel array within the region and then call this function for every pixel we meet. So for the first pixel, we'll give in pixel 1 and take in the average color. Compare these, and this will spit out a value. And this is going to be a difference value. So originally it should be a square root function. So the difference will be calculated by the square root of the distances between these two. But square roots are computationally very expensive. So instead of square root, we'll be using just square and dividing the value by 1000 or 10,000. So after you get the difference, you'll have a threshold value, right? So well, the threshold value will be the difference value that is not too high and not too low, just enough so you can barely see the difference between two colors, right? So while we're going through each pixel, we'll calculate the difference and check if it is above or below the threshold. If it is below the threshold, we keep going and checking for other pixels. If one pixel is above the threshold, so for example we are here, and I don't know what pixel is this, let's just call it 10, and pixel 10 and the average value function, the color difference gives us 38. So it's clearly about our threshold value, which is 35. So 38 is greater than 35. So then we'll call the subdivision function, right? So then we'll subdivide the plane. You can do it in two ways. One, you'll get the x value of this point and divide it through this point, or you can have a random value between the x. So if this is met, the condition is met, it's above the threshold, we'll do a random x value, right? So between 0 and let's say 40, and we'll get a value between 40, let's say it's 20, and we'll divide it here. Now I would recommend doing the random value, because when you have an image that is concentrated to the left side like this one, let's say there's only color here, or I might as well make color, right? So there's color here. So let's say you're going for the x-axis first, right? And I'll keep an x-axis and y-axis here. So let's say you're going for the x-axis here. You'll go through each pixel and compare. Since everything is white, the average will be 0. I'll keep going until you meet this first pixel, right? Let's say this is the highest, so let's this pixel here. And now you have met the subdivision criteria. So you'll get the x and y points of this pixel and use that as a subdivision line. So you'll subdivide it here, right? 1, 2, 3, 4, 5, 6, and you have successfully subdivided. Now after subdivision, you'll give in these two areas for a recursive call with these two new areas. So this will be an area and this will be an area. Remember, we gave in the entire image as the area of the first call, right? Now you'll have this vertex, and starting to vertex. For the second call, you have this vertex and the last two vertices. So this entire area will go for the left hand side or the right hand side of the recursive call, and this area will go for the left hand side of the recursive call. But we'll get to the problem in hand. So you gave this first pixel as the division point. Now we are going for the y-axis. So let's start with this side. So you're going through each pixel and checking for the threshold difference, and again you'll find this pixel meeting the requirement first, so you'll divide it. And this side, there's nothing, everything is cohesive or homogeneous, so this side won't get any division. But when you go for this side again, the first pixel meeting the point is always the same, right? So you'll have more tension or higher thickness of lines in that point, and it'll never change. It won't go past that point because it's simply subdividing, subdivide. So for example, we'll come to this side as well. After the x-axis vertical split, you'll go for the horizontal split. You're going through each pixel in the region and checking for the threshold value. And again, this pixel is the first pixel to go beyond the threshold value, so you'll do a split. And this area is ignored because the entire area is white, so the entire area's average color will be 0 and thus below our threshold value. But when you go on to this area, the first pixel itself in this area is going above the threshold value, right? So you'll do a vertical split again, and as you can see, it comes correctly on the same line, so it will add on to the thickness rather than give you some variation. So that's one thing to keep in mind when you're doing the taking a division solely based on x and y values of the threshold point itself. It would be a different story if you have a lot of colors in an image, but if you're having some minimalist image with just colors on one side of the screen, you'll have lines concentrated to that area, just like that. So let's get back to the random method, which I said again we'll use the concentrated colors. So again we'll go through each pixel and check the threshold difference. And the first pixel that meets the threshold difference is this point, right? We'll take a random XY split. So let's say we'll split here. And after we split here, this area entirely is white, so the average is 0. So we won't bother with this area. Instead we'll go to this area. And again we'll go through each pixel to get the threshold difference. And again the point here, yes, it does show the threshold difference. So we'll get a random y-axis split. So let's say we'll split it here. And this area we're not going to bother because the entire area is white, so the average color is 0. But this side we still have the colors, right? So again we'll do the check. We'll see if there's a color that is beyond the threshold, and yes, there is. So we'll do an X split again, and we'll give a random value, so we split through. Now again I split through the color just for showcase. The random value could come here or here, but the function is still gonna call recursively and you will reach a breaking point. So let's split through the color and we'll ask, okay, this region has color. Yes, there's a difference, so we'll go through each pixel. Since there's a difference, we'll split it again. Random split, we'll split it here. And this region doesn't, okay, this region also has, we'll do a random split. Now this region doesn't have any threshold difference, so we'll let it be like that, but this still has, so we'll do a random split. This region doesn't have a threshold difference, so we'll let it be, and we'll do another random split in this region. And this region has, so we'll split it again, but this region doesn't have, we'll leave it alone. We split, and this region doesn't have, so we'll leave it alone. So we keep going like that. For the first call, depth is 0. Once we split, both the functions will be calling left and right recursive calls will be depth plus 1. So depth will be 1. And for this side, again, once we split, we'll give 2 depth. So depth plus 1 again. So it'll be 2, 2, 3, and it keeps going on. So this is going to be our base case. If the depth is less than our max depth, let's say 20, and 20 itself is too high because if you're calling a depth, it'll be 2 times, right? So it'll be into 2, and is not homogeneous. Homogeneous means there's still a color difference, a color that is above the threshold value. So that is it. That is the basic overview of how this algorithm works. There's one thing to keep in mind. I won't be hard coding everything. I won't be coding everything in front of you. I'll just go over the code that I've already written because there's quite a lot, and I'll try to explain to the best of my abilities. With that said, let's get into the programming section. So welcome to the programming section of this video. I'll be trying to go over each line of code and trying to explain things to the best of my abilities. Let's start with the result itself. This is the result you'll get from this algorithm, and this just using the lines. We'll also be using vector shapes and filling in the colors with average colors and the colors beneath the pixel, and we'll get to that when we go to the tree function. But basically this is the result you have to expect from the k-D tree algorithm. So let's start with the number of functions we have. So we have a preload function, a setup function, a tree function, and this is the most important function here because this will be the recursive function. We'll call each time again and again until a base case is met. We also have an average color, difference, and compare colors, and these are all obviously the sketch I mentioned earlier. We have the average color. We'll take a region, a given region, so we have px and py, the width and the height, and we'll go through that region, get all the colors in that region, and get the average color within that region. And we also have the difference function, and this way you'll get the threshold value, so you'll get a difference based on the squared distance. And we also have the compare colors, which means we'll give a region, and this compare colors will go through each pixel in that region, and if a pixel's threshold is above, the boolean will become true, so the condition is met, and we'll do the subdivision. So let's start with the first function, which is the preload function, which is a built-in function within P5.js, and I've done nothing here except to load the image using the image variable and load image.test, which I've uploaded here in the sketch files. So next to the setup function. So a setup function is basically again a very simple concentration of code here. We create the canvas using the image width and height as I mentioned earlier in the sketch, and we'll also place the image on the canvas calling the image function and the image variable which we have already loaded in the preload function, and placing it at 0, 0, which means this point here. And here is where we'll define the 4 vertex or vertices. So we have v1 here, which is create vector 0, 0, so that point is going to be here, and v2 is going to be width 0, so width 0 is going to be here, and v3 is going to be 0 height, so 0 and height, so it's going to be here, and create vector 4.4 or vector 4 is going to be width height, so which is going to be this point here. And the let average color here, just ignore this for now. I was just trying to debug the code, so I made the average color here, so it's not necessary. So once we have defined our 4 vertices, we make a region. So that region is going to be a new region, which I've made it here in another sketch file or another JS file, which is basically a class region. It takes in 4 variables or arguments, which is v1, v2, v3, and just adds it to the class or the object. So we simply create a new region with v1 here, v2 here, v3 here. So this whole thing is going to be our region. And then we call the tree function with depth as 0 because this is our initial call, and we put the region we just created, which is the entire thing, into the tree function. Now let's get into the tree function. So the tree function has 2 arguments, which is depth, obviously starting with 0, and the region. So first make a node called variable node. This is going to be the node that we are talking about in the KD tree. So this is what we'll be creating by the variable node xy. So node.self is going to be this xy, and node going to create node.self is going to be this xy, and this is going to be node dot right, and this will be node dot left. So this is going to be our node object containing properties of left, right, and self. So once we have that defined, we'll create a couple of variables here, p1, p2, p3, and p4, which is again the vertices from the region. We'll just access them using region v1, v2, v3. And here comes another important part, which is the axis equals depth modulo 2, right? Depth modulo 2, this has to be the length of the vector array, which means if I come here and we have our axis x and y, so this is going to be 0 and this is going to be 1. So if we say depth modulo 2 or the vector length, so for in our example we have only 2 vectors because k dimensional points we have only 2, x and y, so 2. The first call initially is going to be 0 modulo 2, which is again 0. So we'll cut it on the y-axis. So as I mentioned, you might have been wondering why I always cut in a vertical at the first time, because our first call is 0 and 0 is x, so we'll first cut it on the x-axis. The next recursive function will be depth plus 1, so it'll be 1 modulo 2. So 1 modulo 2 is 1 and 1 is on the y-axis. So next we'll cut it on the y-axis. And again 2 modulo 2 is again 0. We'll cut it on the x-axis. and we keep going like that. So that's the reason we use the length of the vector array instead of a constant number like 2, but for simplicity I stuck with a constant. So the next thing, obviously we are taking the average color and calling the average color function. So as you might remember, first we have a region. Our second job is to get the average color within that region. So I assign that to a variable called average and call the average function. The arguments of the average function is going to be p1.x, p1.y, p2.x, p3.y. So p1.x, this x value, p2.x, this x value, and we also have p1.y, right? So this whole vertex, p2.x and or p3.y. And the reason we are using p1.xy and p2.x and p3.y is for a for loop. So the reason why we're using p1.xy and p2.x and p3.y is in a for loop. For going through every pixel, we should start with the first pixel 0 0, and we have to go increasingly like this, like this, like this, like this, like this, like this. So this is how we go through each pixel in a given area. So we'll start with let y equals p1.y. So p1.y is 0. So let's start with 0, and y is less than p3.y, right? So we have to go to the entire, cover the entire region, and the last or the maximum value of y is contained within p4 and p3. So p4 also has the highest value of y, so we'll go through less than p3.y, which let's assume is 50, right? So let's start with 50, start with 0, go until 50 on the y-axis, and y plus plus. And within each of this loop, do another loop for let x. So now it's going to be x is going to be p1.x. So again we start with our starting value 0. X is less than p2.x because the maximum value here is either p2.x or p4.x. So x plus plus. So let's recap. Let's start with y as 0, right? And we'll run the loop until y is less than p3.y, which is here 50. And for every call we are doing on the y-axis, we'll call the loop on the x-axis as well. So for one here, we have to go to the entire x-axis first and then go to the next y. So it goes like this, completed, completed, and completed. So that's what we're doing here, and that's the reason we have given p1.x, p1.y, p2.x, p3.y. So let's go on to the average color function and see what it's going to do. So again we have px, py, width and height. So here we have three variables: average, red, green, blue, set to 0, initialized to 0, and then as I said, we go through each pixel in y order first. So inside this loop, the way we get the pixel is simply by calling image.getXy, and it's important to add this image.getXy because if you simply put getXy, you'll get the canvas color itself. So if you have filled these regions with colors, you'll instead get the color of this region rather than the color within the image. So it's important to keep this image.get in mind. So x and y is going to get the pixel, and you'll get the average red is equal to plus equals the red pixel of, or the 0th value or the first value of the pixel array. So you'll be returned with something like this, right? So p will be something like this. P is equal to So the first value is R, second is G, and third is B. So you say average rate plus equals 255, green is plus equals 255, and keep going on like that. And at last we'll come and get the width and height. So width is equal to W minus PX, and height equals H minus PY. You might get confused because I've already given W and H as the argument, but remember we gave W and H as P2.x and P3.y. So these are essentially X and Y values for a certain vertex, not the width and height. So the way we get the width and height is subtracting the bigger value by the smaller value. So let's say this entire X is 50. So to get the width, we'll have this information here. So P2.x and P1.x is 0. So P2.x is 50 minus 0, again we'll get 50. So what if we split the image and we have this as the P1.x? And here, so it's going to be 25, right? So to get the width, again we'll do the highest value 50 and the lowest value P1.x. Now it's 25, so we'll get 25. 25 is the width, and the same applies to height as well. So the highest height is 50 and the lowest height is 0. So P1.y is 0. 50 minus 0 is again 50. So that's how we got width and height. Now you might ask, why do you need width and height? Well, you need to get the total amount of pixels in the region, and you do that by multiplying the width and height. And once you divide each RGB value with the total number of pixels, you'll get the actual average RGB. And at last, obviously, we return the RGB as one array. So once that's done, so we'll get the average color as an array of RGB, and then we'll get a color difference, compare colors. Now again, as I said, after we get the average color, we have to go through that region and compare that average color with every pixel in that region. And once a pixel has met the criteria of being above a given threshold, we'll call this entire loop. So let's go to our compare colors function and see what it does. So our compare colors takes in two arguments, average color and the region, which has 4 vertices, so vector 1, vector 2 and vector 3, and vector because we have 2 values within that object. So it's going to take as argument 4 vertices of a region, so square or rectangle. So again we do the same thing we did before. We take P1, P2, P3, P4 and we call the property of the region, so V1, V2 and V3 and V4 as the vertices, and then we create a variable called color and bool is false. And once again we loop through the entire region by doing Y first, so we go in this direction, come next, keep going. In this case we won't go till the last point. We'll just check let current color is equal to image.get x and y as we did in the difference function, and then we'll have a new variable called different, which is going to call another function called difference, and that function is going to take in 2 arguments again, current color and average color. So we'll put this average current color array, and we're also given the average color array. So let's see what this difference function does. So now the difference function again will be separating RGB values. So this is simply separating the array into individual RGB values, and the same goes here as well. We'll take in the center value or the average color value and separating into different components. So next we'll define a color different variable, and here's the entire square distance function, right? So first we take RA minus RC, square it, plus GA minus GC, square it, plus GBA minus BC, square it. But in reality this should be, this entire thing should be a square root, but since I mentioned earlier, square roots are really expensive And for something like this algorithm, especially since we're calling the same function over and over again about like 200 times, your algorithm is going to get really slow. So instead of square root, just do a square and return the color different value divided by a certain amount. So that's the function, that's the difference function. It's going to compare two colors and return the difference amount. So this is going to be our value where we'll be performing our threshold. So once we have the difference function, we'll get a value. So this will be the difference value. And we should check if the difference value is greater than our threshold value. So in my case here, it's 5 is our threshold value. If it is above 5, we'll return true. So we'll come above again. So here, so we got the color difference as true or false, right? So if color difference, here's the base statement or base case. If color difference, which means if it is true and depth is less than max depth. In our case, we define max depth as 20. So we'll ask, well, if there is a color difference and the depth is less than 20, then keep calling the function. So here we'll do split 1 and split 2. So I'm going to start here. So this is going to be our P1, P2, P3 and P4, right? Our split value is going to be the split vertices. So if we're going to split, this is going to be our split 1, split 2. So again, as I mentioned, there are two ways to get the split. One is by the way I did here, math flow random p1.x, p2.x. So which means basically we are giving limits of this and this. You can get a random value between these 2 points. So it could be here, so it could be here, 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 or anywhere. Or the second choice is taking the position of the pixel itself. But as we saw, if you're doing something so densely located in one region of the image, you'll just get two lines going denser and denser. So we'll get an x and y by random. So math flow random, the limits here and y as well the same. We won't be using both of them based on the axis. So remember we did the axis in our setup function, or here itself, or not in the setup function, the tree. We got axis. So if our axis is z, so if our axis is z, which means it's 0, we'll just take the x value. So the random x value. The rest will be left to p1.y and p4.y. But in the opposite scenario, if it is 1, the axis, it will become y. We'll take the random y value but keep the p1.x and p2.x. And mind you, when you do the recursive call, these two will become p2 and p4 respectively. And this sp1 and sp2 are just for the first call of the iteration. So with that in mind, let's keep going. So we do the random, we'll get the random split location, and we get the pixel color, which is image.getXY pixel color dot slice 03. And again, the reason why we're slicing is because we get RGBA, but we only want RGB. And you might ask, well, why do you take the pixel color itself? We'll get onto that as we go down. And this is simply for artistic purposes. You don't have to think about this right now. And here's something that's important. As I mentioned, we'll attach the pixel coordinates to the node.self. And here I've attached y. It is kind of wrong because, as I mentioned, we'll not be using the random x and y positions. Instead, we'll be using, if it's in the x-axis, we'll be using random x, but the y of p1 and p2, and if it's, the y of p1 and p4, or p1 and p3, and if it is on the y cut, we'll be using the y random of the y value of the random function, and the x value of P1 and P2 or P3 and P4. So that's something to keep in mind. I've made a mistake here, but since we are not accessing information or we're not indexing or searching on the KD tree itself, we don't have to worry about this. But if you're planning on after you complete the entire recursion and you want to go through the KD tree to find which area is the closest or something like that, you might want to pay attention to this area. So then here is the pixel color, the one we took here. I will get onto that later on. I'll explain why we're taking pixel color and the average color. So we do the if axis is 0, draw a line from x, which we have defined as random, and p1.y. As I mentioned, if it's an x-axis, we'll just take the random value of x. The y values will be taken from the opposite points, so p1.y and p3.y. So here's where we'll be using our fill color, right? I think I haven't explained this in the previous sketch. The reason we are taking pixel color is if there's a difference. So let me come here. Let's say you have green color here, right? And blue color here. Just a little mix with blue as well. And so you're finding the split, and obviously between the first region, which is the entire image, the image is not homogeneous or cohesive, so you split somehow in this area. Now the question is, what color do you fill the areas with, right? So if you want to compress an image, you're not simply going to draw lines, you're also going to fill that area with a certain color. Now the condition is if the average, or if there is no pixel that is above the given threshold, you fill that area with the average color, right? So if we come to this case, let's say we also split in this area or this area, this entire area, the average color is going to be the same. So we'll fill this area with the average color. And even if there's a slight difference in color, the pixel color is going to be below the given threshold, so we'll still fill the area with the average color. But for a region like this, where the difference is above the threshold, you fill the color of the pixel itself, right? So if it is green, the pixel underneath the division is green, or the pixel color, the first pixel that is exceeded the threshold, you'll take that pixel's color and fill it within the regions. So that's what we're doing here. In this conditional statement itself, we are assuming that there is color difference, right? So if there is color difference, it means the pixel color is above the threshold. So that's why we have said pixel color image.get x and y. We'll get that pixels color that is underneath that subdivision area, and then use that color as the color for the fill of the two areas we'll be calling recursively, or the subdivision areas. And then here we use the begin shape, which simply takes p1.x and y, so it's going to be here, p2.x and y is going to be here, and we use p4.x and p4.y instead of p3 is because it seems to go in clockwise manner. So it starts here, goes here, and comes here, and then it comes here, and it is close to the shape, right? So next again we do the split here, x p1.y, x p3.y. So let me better illustrate this in the code or the sketch here. So the split is going to be p1.x, I mean p1.y, sorry, and x p3.y. And I think it's pretty clear why we chose those variables, I mean those values. We chose x because x was caught in random, and this is the x-axis, so we need x to be the same in this graph. So x same point, p1.y, because we have a starting point here, p1.y is 0 and p3.y is the last or the maximum y value in this region. You could also take p4.y, and that becomes our split region. So when we do a recursive call, the new region is going to be this and this. So the new region will be P1, SP1, this point, this point, this point, and this point. And likewise in the left right hand side it will be SP1, P2, SP3, SP2, and P4, right? So that's what we have done here. We made the split vertices here, or the split vertices, and then as I said, we create a new area, which is area right and left, using P1 split 1, P3 split 2, split 1 P2, split 2, and P4. And then at last we also add our properties to our object, node object, which is node.left is equal to tree, depth plus 1, which is 1 again, and area left, and we given the new region area left and area right, and it keeps going until the conditional statements are met. And then obviously we also have an else statement if the axis is 1, which means we are doing a cut on the y-axis. We'll be using the x values of the opposite vertices, and we'll be using the y value of the random function. And the next are pretty much the same as the above. We do node.left, add a property as, and call the recursive call again here. We add one more depth, give the region new region, and we do node.right and give the new region, and it keeps going until the base statement is met. So what happens when the base statement is met? That's what we have here. So this is if color, there's a difference in color and depth is less than max depth. If max depth is reached and there's no color difference, we'll call this function here, or this line of code, which is filled with the average color. As I mentioned earlier, if there's no difference, we'll just fill it with the average color, and it's pretty much the same. We'll just begin shape and end shape with the vertex in mind. So that's pretty much it. Let's render it one last time without the lines. I don't know if you can see it, but here is the result. I'll display it on the screen. So with that being said, thank you guys for watching. If you guys enjoyed the video, be sure to like it and do subscribe. We have been popping up lately. We are around, I don't know, 40 subscribers, and I'm really grateful for each and every one of you. This channel was supposed to be like a learning channel for me. I learn interesting topics and reinforce those topics by making videos on those topics. But it seems like this channel has the potential to become a niche channel. So I'm really excited about it. With that being said, I'll see you guys in the next video.